Howdy y'all, and thanks for dropping by. This may be my last video about the odd misconception that what most folks think of as gravity is actually caused by relative density. There are other things to talk about, but I think I might have one last thing to contribute. I may also make mention of a flat earth meme about black swans. I don't think that meme will stand the test of time, so I should explain. As I record this, flat earthers are concluding that if you can ever see farther than geometric calculation says you should on a spherical Earth, then the Earth can't be spherical. If you find one black swan, they say, you've disproven the assertion all swans are white. The trouble is, what color is a white swan when you look at him in the dark? How far away is the horizon when what you see is changed by refraction? Do your eyes always tell geometric truth? The short answer to that last question is no. YouTuber Nathan Oakley goes so far as to say that if refraction can let you peek around a curve, it can, then that means there is no geometric horizon. It's really a silly argument. Physical geometry isn't changed by optical illusion.
The kill shot, the black swan.
In Nathan Oakley's BS photos, and by BS I mean black swan, a tangent to the globe would be seen as a line bowed down to touch the water a little over a mile away from the observer on the beach, warping back up and out into space. The line would be ruler straight. It would appear curved. If you think it's abusive to physics to bend light, then don't wear eyeglasses. That's what they do. And honestly, a little myopia makes flat earth theory easier to understand. Experience and presbyopic they are not. If none of that makes sense, I envy you since you haven't been pestered by absurd black swan theories. But back to the subject at hand. If you haven't heard about this before, it's true. There are folks out there who believe things fall down not because of gravity, but because of relative density. Newton's apple was denser than the air around it, and that's the only reason it fell. Or so some people say. Richard Feynman had an opinion about that kind of assumption. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. I submit that Newton was wrong by a tiny bit about gravity. Einstein, I suspect, is also wrong to some degree. Flat earthers are completely wrong about gravity. They say gravity isn't a force. Well, centrifugal force isn't a fundamental force either. It emerges with rotation. By the way, I'm going to jump out on a limb here. I'm not a physicist, but I would like to point out the common slang would have me say centrifugal force emerges in a rotating frame of reference, but that doesn't seem quite correct to me. A frame of reference is a coordinate system. If you appreciate tedium and painful mathematics, you can describe motion on a stationary object in terms of a rotating frame of reference. There's no reason, other than love of life itself, for the lines of latitude and longitude on a planet to be stationary with respect to the surface. The planet could be stationary and the lines could rotate. The coordinates of any particular spot would be constantly changing with the motion of the coordinate system. In that rotating frame of reference, there would be no Coriolis and no centrifugal force. That would be insanity, of course. But it would still make more sense than relative density as a force, a tired concept which seems to be re-emerging as the black swan arguments get more and more beaten up. Flat earthers describing gravity in terms of density makes as much sense as describing ink blots by musical pitch. I would say it's a little like describing bureaucratic regulation in terms of smell, but there actually is some validity to that. It is quite true that the genesis of gravitational force isn't known. Newton cautiously suggested that mass attracts mass because that's what appears to happen. Einstein said that mass curves spacetime, causing mass to experience a force toward other mass. I accept that's been very useful in a situation where Newton fails, but I've got no more than vague notions of what constitutes curved spacetime. I do know exactly what gravity will do outside of specialized circumstances like the innards of a black hole. Here's YouTuber Sleeping Warrior describing helium falling up, or something. The quotes displayed are points he disagrees with.
We know that if you let go of a helium balloon, it doesn't fall down. It falls to the sky. So what's attracting it, or what force is pulling it or pushing it towards the sky? Ballers explain it with buoyancy, dependent on gravity being a force, Well, we know that a helium balloon will rise to the sky not because a force is pushing it, but because it's in a state of disequilibrium, because it's not in harmony with the medium it's in. It's in disequilibrium. It will find its level if it's free to move. This is demonstrable time and time again.
Sleeping Warrior says a helium balloon rises because of disequilibrium. In this quote, he says it's not because of any forces acting on it. Other times, he said that density differential causes or is a force. In all cases, there isn't any offer of supporting evidence. Here, he says it's demonstrable time and time again that gravity isn't involved. Let's take him at his word. We'll set ourselves up for humiliation. I hate high self-esteem. This will be fun. If the operative force behind the phenomenon of things floating or sinking is relative density disequilibrium, then it should be impossible to predict whether something will float or sink without knowing its density. Sleeping Warrior agreed with me. There you go. A leading expert in the field of relative density says I have to know relative density. But let's up that ante just a bit, shall we? Let's use gravity. Sleeping Warriors often said that won't work. So let's assume gravity is real. That ought to really put us behind the 8 ball, and let's turn 9.8 meters per second squared on its head while we're at it. We'll treat gravity like 9.8 Newton per kilogram. You rarely hear gravity described as force per mass. It's always distance per time squared, but force per mass is a handy way to look at it. As per my chat post on Sleeping Warriors channel, we'll ignore the density of the objects we're floating and sinking in our tests. That's got to torpedo all hope for us, but on top of that, we're going to ignore the density of the medium and the relative density between the two. We won't even test how fast a reference object will sink or float. Nope. This is nothing but feckless math. Of course, to fully comply with my claims, we have to ignore the volume of the object too. Okay. We have farcical-old gravity. We don't know volume of any objects. We don't know the density of the medium. We don't know the density of the objects. And we have no clue about the relative density equilibrium between the two. And let's make it harder. Let's not just predict whether something will float or sink. Let's predict how fast it will float or sink. And test our predictions. That should pretty well screw up our analysis. Let's have a go at it anyway. Here's the setup. We'll use a couple of small bottles ballasted with BBs, and we'll predict how fast the bottles will float or sink. We'll predict to the tens of milliseconds how long it will take them to float or sink based on fractional gram measurements and the presumed force of gravity. Then we'll measure what happens to see if we were right. Note there is some variance in the size of the object we'll use in this demonstration. These are cheap travel bottles sold by Walmart, my best local source for lab equipment. They aren't precision made. They are for travelers who want to carry a bit of shampoo, or real poo for those who don't think shampoo is good enough and insist on the real thing. Note in the relative density camp, contrived values are as close as they get.
Pick any two objects, any two mediums that are next to each other, and give them arbitrary values, relative numbers that are one would be, let's go with we'll say the top one. We'll give it the value of 1. And the medium that's below it will give it the value of 2. Let's say we've now got a syringe full of a fluid and its density is a known 1.5. If we do a drop test and drop it in there, it's going to find its level between the two levels.
Science, these flat earthers like to say, starts with an observed natural phenomena, even if observations aren't quantified. In their limited and terribly incorrect view, nothing created by humans is natural enough. Lead objects in Mr. Cavendish's garden shed don't obey natural law because they aren't hanging from cannonball trees or something like that. May I humbly suggest that observations in a swamp, at the laser interferometer observatories, even of man-made elements in a particle accelerator, are all scientific observations if they are made with scientific rigor, and they all showcase things acting in accordance with nature. Made-up numbers are not, no matter how lovingly they are applied to anything. Hopefully, in contrast, with intolerances, we're going to hit some numbers pretty much dead on. Note that we will be slicing forces down to the fraction of a gram. If there's anything off in these methods, we're not going to be able to predict to the gnat's eyelash. But I think we can. Oh, good grief. I already see a problem. I specifically ordered a black swan. Instead, I've got a little ducky. Dadgummit, this is no way to run a railroad. In my defense, I would like to point out the file box to the right contains an annual audit report I prepared for an organization I serve when I'm not developing software, writing, or grappling with cosmic forces in my living room. Newton was once master of the Royal Mint. He did his share of bookkeeping too, at least when he wasn't developing new branches of mathematics or grappling with cosmic forces. And except for Newton's IQ, Newton's initiative, and his accomplishment for the ages, I feel a close kinship. Anyway, here is some unknown volume of the fluid we'll be using in our tests. It's tap water. Since we're going to be cutting things really fine, you would think it would be nice to know the precise density of the water. It's close to 1 gram per cc, but not exactly because of mineral content. Whatever it is. We'll never know because we're not going to check. It doesn't matter. We're ignoring density. Whatever we've got here weighs 314.62 grams. Now let's take one of our bottles and suspend it in the water. For giggles, it's chock full of BBs. I don't know the density of the object, other than it's got to be a whole boatload more than the test objects we'll be preparing. I have no clue what it weighs. I never checked. If relative density means anything, this next measurement means nothing. But we're going to rely on it like kindergartners trusting Santa Claus. Anticipation of our impending humiliation ought to bring great joy in the Flat Earth camp. With the hideously dense object of unknown weight, unknown density, and unknown volume suspended in the water, we see a new weight of 437.08 grams. I say that's due to gravity and increased potential energy stored in an elevated water level. Some would say it's the force of relative density, or maybe just say it's not in the natural world because I touched it. If this new weight is due to densities, then this measurement is out of context for everything else we're doing and completely meaningless. What the heck? Let's go with it. The weight increase in the wire used to suspend the bottle using my same tired old laughable techniques was 0.44 grams. I'm going to conclude the buoyant force on this object is 122.02 grams. Now let's ballast a couple of bottles. One will be a smidgen more than 122.02 grams, the other will be just a bit more than that. The BBs vary in weight, generally between 1/4 and 3/10 of a gram. The first object we'll call the blue object from the color of its cap. 122.76 grams seems as good a place as any to stop, just a bit over the 122.02 grams of buoyant force we're expecting. The red object gets ballasted to 123.28 grams, basically a half gram more than the blue object. Think a half gram out of 1/8 of a kilogram will make any difference? I do, based on the attributes of gravity and the weight measurements taken in a completely different relative density context with that bloated, overdense initial object. Here's the math behind what I predict. Note that the grams read for the buoyant force is corrected to dynes by multiplying by 981, which is the acceleration of gravity in centimeters per second squared. Being a slacker, I made a spreadsheet to do this for me, including the depth of the water in our test tank and the height of the objects. I'll release them even with the surface of the water, so they will bump the bottom in the depth of the tank less their own length. Based on net acceleration and length of drop, we predict the blue object will drop 25.4 centimeters in 2.93 seconds. The red object will take 2.25 seconds. And now, it's sink or swim. I used the frame-by-frame elapsed time display in Apple Motion to time the drop. The blue object took 2.88 seconds. I was off by 1.77%. Given my cousin Eddie level of lab sophistication, that's a bullseye. The red object was predicted to take 2.25 seconds. It took 2.28 seconds for an error of 1.28%. Another bullseye. Sleeping Warrior doesn't think gravity accounts for things that float, though. Do you suppose calculations that are based on how hard things land on the bathroom scale will say anything about how fast things float up in a fluid, investigation is mandated. Again, weighing the effect of every single BB going into the containers and how far I've personally sunk in this business of flat Earth, we ballast our blue object to 121.14 grams and our red object to 121.57. My method for release this time was to tie the test object to an improvised anchor. I measured the height of rise, entering it into the spreadsheet, basing the measurement from the lowest extremity of the object to the surface of the water. That was a little cumbersome, but I'd already invested a little time in the spreadsheet, and that's how it worked. The objects were released by reaching into the water with scissors and cutting the fishing line. I hasten to point out, if my wife is concerned about her sewing scissors being used in the Flat Earth test tank, there's nothing to be worried about. Besides, whatever scissors were used are too blurry in the video to be entered into evidence. Despite my dedication to follow the truth no matter where it leads, there's just no way to know who used which scissors underwater. The blue object was predicted to rise 13 inches in 2.39 seconds. It took 2.28 seconds for an error of 4.74%. The red object was predicted to rise 12.5 inches. Its tether was a little longer than the blue object. That was predicted to take 3.24 seconds. It actually took 3.35 for an error of about 3.3%. Part of the reduced accuracy in the float times, I believe, came from difficulty in getting a precise depth measurement. When my tape measure touched the top of a test object, the object would bounce around. Made it hard to get a precise measurement. The takeaway from this is that gravity pulling down really is why helium balloons float. And of course, be careful when arranging Craigslist purchases. You order one thing, you might get a duck of a different color. If I were a cruel man, I would leave it like this. Transparency requires I reveal why the trick questions were tricks. When I measured the increased weight of the water caused by immersing an object in it, you could say I measured the density of the fluid. It was 122.02 grams per bottle volume. When I set the weight of the bottles I released in the water, you could say I was setting their density. But there's a problem with thinking those densities were the driving force. I would measure the same 122.02 grams of buoyant force even if the test bottle were full of air and I had to force it under the water. Half full of BBs and it drifted down, or completely full and wanted to sink like a boat anchor. Each measurement I took was weight in a downward direction, and the math worked identically for things that float and things that sink. That's because the only real force in the situation was gravity, acting on mass, giving it weight. The mass involved was the water and the test objects. The density of an object has nothing to do with the buoyant upward force acting on it. Try it. Put a glass of water on a reasonably accurate digital scale. The scale I used here cost $12. Dip 4 inches of a No. 2 Phillips screwdriver shaft into the water. Make sure you don't touch the sides or bottom. Note the weight increase. Now dip 4 inches of a 1/4 inch wooden dowel rod, which is roughly the same diameter as a Phillips screwdriver shaft, but obviously a different density. The weight increase will be the same. That weight increase is exactly set by the volume, not the density of the object you submerge. Push 10 cc's of anything underwater, and the water will pick up 10 grams of weight because 10 cc's of water weighs 10 grams. The Earth, by the way, is spherical. Thank you for visiting. If this sort of thing floats your boat, be sure to use a real Newtonian force on your mouse to click subscribe, like, and the notification icon. If you try to click your mouse by applying relative density, you'll just get nowhere.